Hello, AP Calculus students. We're getting to the end of this. Sometime pretty soon I will see you again in person, I hope. And I don't know, that's what I have to say about things. We are starting to look at the final section of Unit 7 about u-Substitution. And this is kind of a different story than what we did in 4.4 about first and second fundamental theorems of calculus, functions defined by integrals and all that. We're going to go back to antiderivatives now. And basically, this method that we're going to learn about will be our way of undoing the chain rule. U-Substitution is all about undoing the chain rule. How we find the integral of something with something inside it, composition problems, well, sort of. And this will let us, again, deal with some sort of composition problems. So to get us started, we have our chain rule that says the derivative of f of g of x equals, okay, the derivative of the outside, f prime, leave everything inside there, f prime of g of x, times the derivative of the inside times g prime of x. We have a theorem that says if I want to find the integral of f prime of g of x times g prime of x dx, if I want to find the integral of this, if I want to figure out what has this thing as its derivative, well, I know what it's going to have to be. It's going to have to be just that thing. Really just chain rule in reverse. I think this is sort of obvious. Derivatives and integrals do the opposite of each other. But I don't think it's super clear at the moment why this is a useful theorem. So what we're going to talk about is a trick for how to integrate composition problems called u-Substitution. Basically like how this theorem works and then how we can apply it. The next 5 minutes, I'm going to warn you, are going to be a little bit of kind of theory, how this stuff works. Please do stick with me through this. It is important that you see how this method works. Then we're going to spend the rest of this video just looking at examples. So do stick with me through the beginning of this. This is our trick called u-Substitution. I want to try to figure out the integral of f prime of g of x times g prime of x dx. I know what it has to equal, but I want to see why it actually equals that thing. So I want to try to integrate the derivative of something with some other function inside there times the derivative of the function that's inside there. Step number 1. I want to determine which function is what I'm going to call my inside function. Let me start by just saying that. Determine which function is the inside function. Which function is my thing inside? Well, I kind of see something inside here. In general, there is a hint. The derivative of that thing should also be showing up in your problem. Hint. Its derivative should show up. And what I'm going to do is I'm going to call that u, hence the name u-Substitution. Determine what function is the inside function. Its derivative should show up. I'm going to call that u. Well, I see an inside function here. It's g of x. I'm going to say that u equals g of x. The second thing I'm going to do is I'm going to calculate du, the derivative of u, just in differential form. Calculate du. the derivative of u in differential form. Step number 2, calculate du, the derivative of u in differential form. Okay, so du equals, what's the derivative of g of x? Well, g prime of x dx. Now, why am I doing all of this? I'm doing all this stuff so I can rewrite my problem in terms of u and du rather than in terms of x's. Step number 3 is going to be rewrite the problem in terms of u and du. And then when we're done, we'll integrate that thing because it'll be something we actually can handle. I'm going to rewrite my problem in, whoops, you can't see that, sorry. I'm going to rewrite my problem in terms of u and du, and I'm going to integrate. What I mean here, I'm going to replace this thing over here with u. I'm going to replace this whole thing, g prime of x dx, with du. I guess that pen's running out. Okay, that's going to give me the integral of f prime of u du. And this is something I can handle. What's the integral of f prime of u du? Should just be f of u, plus a constant, of course. Step 4. My original problem had x's in it, so I need x's in my answer. I'm going to replace the u in the final answer with what u stood for. Replace the u in the final answer with what u stood for. Sorry, again, you can't see that. Zoom in a little bit. I'm going to replace the u in my final answer. Come on, let's focus. With what u stood for. I know u is g of x because I said that in the beginning of the problem. So I'm going to get f of g of x plus a constant. I want you to take a moment, make sure this is copied down. We're going to spend the rest of this video seeing how this is actually useful and really important to us. Okay, here we go. First example. I would like to try to do the integral of 2x times x squared plus 1 to the 4th dx. And the first thing I need to do is decide what my u will be. My u is my inside function. I think my inside function is this x squared plus 4. So I'm going to say that u equals x squared plus 4. Then I'm going to calculate my du, my derivative in differential form of x squared plus 1. The derivative of x squared is 2x dx. Derivative of 1 is 0. I'm going to say that du is 2x dx. I originally said in the beginning that u should be the inside function whose derivative also shows up. Well, I think I see the derivative showing up. That's that 2x over there. I can now rewrite this problem because this whole thing over here, that's just u. And my 2x and the dx together, those pieces make up my du. I can rewrite this problem as the integral of u to the 4th du. And I get something much easier that I can handle. This is our u-substitution trick. I'm now going to go and I'm going to integrate that thing. I'm going to integrate u to the fourth du. I'm going to get 1/5 u to the fifth plus a constant. Only problem is the original problem had x's in it, which means my answer needs to have x's in it. So I'm going to say 1/5 times x squared plus 1 in parentheses to the fifth plus a constant. This is my integral of 2x times x squared plus 1 to the fourth dx. If you don't believe me, go find the derivative of this thing. 1/5 times 5 times x squared plus 1 to the fourth. Yeah, that's going to give me this part over there. And by the chain rule, I'd multiply by 2x. Yeah, that's the piece that I have over there. This is how we integrate composition problems where there's an inside function whose derivative is also showing up. Let's try another. Let's try the integral of 3x squared times the square root of x cubed plus 1 dx. I need a u, the inside function whose derivative also shows up. What should u be? I'm going to try making u this thing that's under my square root. I'm going to make u x cubed plus 1. Okay, if u is x cubed plus 1, we need the derivative of this thing in differential form. What's du? What's the derivative of x cubed plus 1? Derivative of x cubed, 3x squared dx. Derivative of 1 is 0. Oh my goodness, what do you know? I've got that thing showing up over here. That's my du, and the thing under the root's my u. I can rewrite this problem as the integral of the square root of u du. And of course, rather than dealing with that, I'm going to make it the integral of u to the 1/2 du. See if you can finish this. Integrate, get an answer in terms of u, and then just replace the u with the x thing that it stood for. I'm going to get u to the 3/2 over 3/2 plus a constant. This is 2/3 u to the 3/2 plus c. This is, am I still on the screen? I am still on the screen. What do you know? 2/3 times x cubed plus 1 to the 3/2 plus c should be your final answer. I'm picking out the inside function. I'm going to make that my u. I'm going to find its derivative, and hopefully that derivative is going to show up in my problem. If it does, that's my du. I'm going to go and rewrite this thing in terms of u's and du's, and then I'm going to integrate. One more like this before we make them a little bit trickier. Let's try something like this. The integral of the secant squared of x times the tangent of x plus 3 dx. I don't think it's super easy to see an inside function and an outside function. So maybe the better way of thinking about this is u should be the function whose derivative also shows up. What do you think u is going to be? If I make u this entire thing over here, if I make u the tangent of x plus 3, its derivative is derivative of tan x, that's secant squared x dx, plus 3, derivative of 3 is just 0. I've got everything I want. This thing over here, that's my u. This mess over here, that's my du. We're going to get the integral of u du. See if you can finish this. Integrate, and when you're done, replace the u with the x thing. U squared over 2 plus a constant, so 1/2 times the tangent of x plus 3 in parentheses squared plus a constant. If you try to find the derivative of this, you're getting that problem back. Now, here's the problem. Actually, you know what? I'm not even gonna tell you the problem. We're just gonna move on and do another one. The integral of x times x squared plus 1 squared dx. I want you to figure out your u, your du, and tell me what's wrong. I think my u is this inside piece over here. I'm going to make u x squared plus 1. Its derivative is 2x dx. Oh, wait a minute. I want 2x, I only have an x. Sometimes this is going to happen when your du is actually correct in terms of the variables, but the constant is a little bit off. I have a 1x, I want a 2x. Well, here's what we can do, and I'll write down this trick in a moment. I want a 2x? Well, there, I got a 2x. Of course, you're not allowed to do that, but if I multiply by 2, and at the same time, I multiply by 1/2, then I am allowed to do this. I multiplied inside my integral by 2, canceled out that 2 by multiplying on the outside by 1/2. I'll write this trick down in a moment, but here's what I'm now allowed to do. Now I see this thing over there, that's my u. This 2x dx is my du. And up front, I just have a 1/2. I'm going to get 1/2 times the integral of u squared du. I can integrate this. 1/2 times the integral of u squared is u to the third over 3 plus a constant. This is going to equal 1/6 times u cubed plus c. 1/6 times x squared plus 1 cubed plus a constant. Here's our trick in words. Oh, you know what? I think I need this on a new page. Take a moment, finish copying that down. Okay. So here's what's going on. Sometimes our du isn't exactly what we want. Sometimes our du isn't exactly what we want. Or maybe rather than what we want, what we have in the problem. If our du is what I want other than the constant, if it is what we want other than the constant, we can multiply inside the integral by a constant and then cancel it out by multiplying outside by its reciprocal. We can multiply inside by a constant and cancel it out by multiplying outside the integral by its reciprocal. Or rather, by multiplying outside the integral by its reciprocal. And this will actually be the case in many problems. It's not going to be exactly what we want, but we can adjust it by doing this constant trick. Please copy that in your notes, and then we'll look at a few more examples. Okay, let's try this one. Let's try the integral of x squared over the square root of x cubed plus 1 dx. You go tell me what the u is and what its du, its derivative, is. I'm going to try making u that inside piece from the denominator. I'm going to make it x cubed plus 1. Its derivative is 3x squared dx, which is kind of what I have. I have an x squared, I want a 3x squared. I can make this problem work by sticking a 3 inside my integral if I cancel it out with a 1/3 outside my integral. This is going to give me 1/3 times the integral of this whole thing is a du. I'm going to get du over the square root of u. How about you see if you can finish that? Go rewrite that so it's a u with a negative exponent, integrate, and replace the u with x cubed plus 1. So I'm thinking 2/3 u to the 1/2 plus a constant. I am thinking 2/3 times x cubed plus 1 to the 1/2 plus c. Why don't I be fancier than that and say 2/3 times the square root of x cubed plus 1 plus a constant. Let's take a look at a couple more. Integral of the secant of 8x times the tangent of 8x dx. This one's a little weird. Any thoughts on u? This one's a little tricky. I try u is the secant of 8x. I know the derivative of secant is a secant tangent. That's not going to help because I don't have another secant in there. If I make my u the tangent thing, its derivative is secant squared. I don't have a secant squared. My u is actually just going to be 8x because its derivative shows up other than the constant. Its derivative is 8 dx. Well, yeah. This is showing up other than the constant, other than the 8. Yeah, I've got the dx and nothing else. I can stick an 8 inside here and a 1/8 outside there. Then, this thing is my du. I've got a u, I've got another u. It's okay that I've got two of them. 1/8 times the integral of the secant of u times the tangent of u, du. It's been a little while since we've done this. But the integral of secant u, tangent u, that's going to be secant u. The derivative of secant is secant tangent, so the integral of secant tangent is secant. Final answer here, 1/8 times the secant of 8x plus c. If you found the derivative of this using chain rule, you'd get that original problem back. One more. Integral of 7x to the 5th times the sine of x to the 6th minus 2 dx. What's u? What's du? What's wrong? I'm going to make u that inside piece of x to the 6th minus 2. Its derivative is 6x to the 5th dx. What's wrong? I want a 6 and I've got a 7 in there. There are ways we can do this with fractions, but I don't feel like thinking that hard. How about I just take this 7 constant and just move it out front, because I'm always allowed to do that with a constant. And I can make this just the integral of x to the 5th sine x to the 6th minus 2 dx. This is not u-substitution work. This is just, it's a constant, pull that out front. Now let me go and deal with my u-substitution. I said u should be 6x to the 5th dx. which means I need a 6 inside, and outside, I need a 1/6. See if you can finish this problem. This is going to give us 7/6 times the integral of, okay, that's du, there's my u. We're integrating the sine of u du. That's 7/6 times the negative cosine of u plus a constant. Negative 7/6 times the cosine of x to the 6th minus 2 plus a constant should be your final answer. There is one other thing I just want to show you very, very briefly. This rule lets us deal with a whole bunch of composition problems that we couldn't have handled before. Problem is, there are still some composition problems we can't integrate. For example, if I ask you to integrate x cubed plus 2 squared dx, or if I ask you to integrate x times the sine of x to the 4th minus 2x dx. In this first one, I'd make u x cubed plus 2. Its derivative is 3x squared dx. It's not a problem that I don't have the 3, but it is a problem I don't have the x squared. U-substitution isn't going to work here. Over here, if you try that, u equals x to the 4th minus 2x. Its derivative is 4x cubed dx. The 4 is not an issue, but the x cubed is. You're not allowed to multiply by variable things inside your integral versus outside. Not allowed to do that, only constants. Can't make that work either. We can't do these integrals. Actually, we could do that first integral. This first integral, we could have done this when we first learned about antiderivatives. We could FOIL this thing out and then try to integrate that thing. Thankfully, it was just a square, not a 5th or a 6th. Otherwise, we do have a lot of foiling to do. But right now, there's really no way to deal with this problem over here. As you move through calculus, not this year, but higher calculus classes, you'll see maybe some tricks that will let you deal with things like this. But for right now, we can't handle a problem like that. We have one last video, which will be next week. Actually, I might make 2 videos out of the topics for next week. We need to see how to do definite integrals with a u-substitution, and then one little variation on u-substitution called change of variables. That will be last week. That will be not last week. That will be next week. That will be the final assignment of term 2, and February 1st, term 3 starts, and we're back to calculus in person, sort of in person. As in person as anything is going to be this year. I don't have anything else for right now, so I will see you, well, I won't see you, you will see me next time.